Hi there, this is the third part of a set of videos building an environment monitoring station using Pimoroni's Enviro Plus board. In the first two videos I covered the hardware and making the front cover to get the unit you see here. In this video I'm talking about the software. I realize that this is a bit tedious for most who are not interested in software architecture, drivers and the like. So I won't blame you if you rather skip this one and go directly for the installation and usage videos. Still here? Great! I promise I won't go line by line over 1000 plus lines of code, just some architecture and a few things that are maybe a bit unusual and need a word of explanation. Let's start by looking at the Python files you can download from my GitHub page. I'm using this view here, showing them as packages. Each of these is a file, just imagine the .py attached to the end of the name. The main program group are these four, which deal with running the show and the user interface using touch sensors. All sensors are implemented by extending from a base class sensor item, which defines what a sensor looks like software-wise and what capabilities it has, in particular what statistics are kept. And here are those sensors, a package for each. I added some color coding. The yellow indicates that this package contains a Python class or group of classes, and the orange indicates it's not only a Python class but also a driver for directly interfacing a sensor. No color means it's just a normal Python module. The names you see in the yellow and orange packages are the class names. In some cases there's only one and it's identical with the file name. In other cases there are many classes in the same package. If you count the orange driver packages, you see only 3, but there are many more sensors. That's because what you see here are just the packages I wrote myself. The Enviro station also uses open source drivers from Adafruit, Pimoroni and others that need to be downloaded and installed from their respective sites. A more complete view is here, which also shows the principle how these packages are used in the Enviro station. Even though this required major rewrites, I selected this architecture for the sake of stability and long-term maintainability. There are 5 sensors, including the touch interface, that are all connected to the same I2C bus, so I made sure that these are all using the same underlying I2C interface. Since the majority are supported by Adafruit, I chose their architecture for doing this. Even the drivers I wrote are now using the functions of the Adafruit I2C device to use the I2C bus. Doing it this way avoids any problems with bus contention and different drivers messing each other's I2C communication up. This is not just theory. In the first version of the Enviro station, I had at least 3 total different drivers all using the I2C bus, and while that seemed to work short term, I experienced random crashes with I/O errors on the I2C after 4 to 8 hours of continuous operation. This problem has gone away with this new architecture. A carefully designed choreography like this requires that all sensors are being used one at a time, and this rules out using multi-threading or tasking, because if you would use such an architecture, deterministic I/O timing across multiple sensors would be really difficult to guarantee. Some of the Adafruit drivers, for example, use the odd sleep statement in a few operations, often just for 5 milliseconds and usually commented with something like, "Just to be sure the chip has finished doing whatever." Such a tiny sleep statement buried somewhere in their code would be enough to allow a thread switch right in the middle of an I2C operation. Avoiding this gets messy, and in any case, tasking would not gain anything in performance on a Raspberry Pi Zero, on the contrary, due to the overhead of having to use thread-safe data structures. And while we are at design principles, here are the other 2 important ones for the Enviro station software. In a lot of cases, a sensor chip provides actually a bunch of related measurements shown here symbolically as A and B. Think of the BME 280, which provides temperature, pressure and humidity, or the LTR 559 ALS providing lux and proximity, and so on. A good design principle is to read all this data in one go from the chip into local memory into something I call a poll operation and give it a timestamp. Then additional functions can be called as often as needed to separate that data into individual measurement values or do the statistics and so on without occupying the I/O bus and the chip because they are using the local copy. This has the additional advantage that those different measurements like pressure and humidity have indeed been measured at the same instant. This would not be guaranteed if after reading, for example, pressure, the driver would go and fetch new data from the chip when you ask for humidity. The diagram on the right shows how the main program works. No tasking or threading is going on here. Instead, the Enviro station uses a deterministic loop, which you see here, where each sensor is dealt with one at a time. This deterministic way makes it very easy to debug and verify performance. The design goal is to do exactly one measurement cycle for all sensors per second, but a loop with that frequency would make the user interface appear very unresponsive. So the heartbeat is set to half a second and the sensor poll and recording is done every second heartbeat. It is easy to check if that design goal is reached because the software measures the elapsed time from top to bottom of the loop. If that is less than half a second, say it only uses 300 milliseconds, it executes a sleep, in this case for 200 milliseconds before starting again. It is easy to verify performance because if that delta sleep time would be negative, the design goal has been missed. A simple print statement can be used to check that during development. On my Raspberry Pi Zero, the CPU is usually loaded only 25 to 30%, so no problem. From my previous videos on the Enviro Plus board, you already know that getting the MEMS microphone to work is not easy. You will notice that I abandoned Pi Audio and used a sound device package to access audio from Python. This in turn requires libport audio 2 to be installed, and we still need to compile I2S support into the kernel and install a simple microphone driver. Luckily, this is now a lot easier thanks to a neat script from Adafruit. Sound Device provides a very straightforward interface to handle incoming streams of PCM audio data from the microphone in a callback function. That is kind of multi-threading, so strictly speaking, my previous statement that Enviro Station isn't using that stuff isn't quite true. But since the MEMS microphone is the sole user of the I2S bus, the multi-threading is not causing any problems. It does mean, however, that we have to use thread-safe queues for audio data. The ST7735 driver is the original from Pimoroni and it uses its own ways of talking to the SPI bus. I tried to use the Adafruit version despite its lack of decent documentation, and by studying the driver code I got it sort of half working in that the content appeared but the colors were all wrong. In the end it was just too much work and I decided to keep the Pimoroni version. Like the MEMS microphone, a different driver is okay in this case since the ST7735 uses SPI and not I2C for communication. One last point, you may have spotted that there are two drivers for the MPR121, an Adafruit one and my own. Originally I abandoned my driver and used the Adafruit one, but I found it a little less responsive and reverted back to mine. The code has both still in and you can comment out the one you don't want to use. I suspect the difference in performance is because the Adafruit driver does not do auto calibration at startup. In any case, the difference is tiny and might quite possibly be only in my head. If we go briefly back to this diagram, you see that there are lots of classes in the Enviro station, many more than what you ordinarily might expect. All the names in the yellow tag packages are classes. Some have only one, but for example the sensor LTR559 package contains 3 and the sensor PMS5003 10. That seems like an awful lot of code, but in fact it isn't. Apart from a comment header at the top, here's the complete content of the sensor LTR559 package with the 3 classes it contains. You see that all 3 classes extend the base class called sensor item, and in most cases contain nothing but a simple one-line constructor. This is the same for almost all the other classes. To understand what's happening here, we need to look at a class diagram. This is not a complete diagram, since I only added 2 real sensors, the MC9808 and the LTR559, but the others follow the same principle and would just clutter the picture even more. The basic idea is that we have a generic abstract class called sensor item that defines what each sensor is supposed to look like for the Enviro station. So we have a function that returns the sensor value, one that returns sensor statistics. There's a configuration function in case we need to change the configuration, and of course there's the poll function that fetches new data from the sensor. However, as this is a generic, none of these functions do anything in this class. However, it implements all the hooks into the statistics package by creating a stat item for this generic sensor. The statistics capabilities come from the class stat item, which implements a bunch of statistics functions such as average, min, max and trend, plus an add sample which adds a new value and its timestamp into the buffers necessary to do the statistics calculations. Those in turn are realized by 3 ring buffers from the ring buffer class. More about this in a moment. A real sensor like the MCP9808 will simply extend the basic sensor item class and automatically inherits all its functionality, which makes it very compact. The only code necessary is to override the pull function to talk to the real driver for the MCP9808 temperature sensor, fetch the current temperature and add it to the statistics. The MCP9808 configuration is done in the constructor, and so no on-the-fly reconfiguration is necessary, and the inherit configure function is the one from the base class and does nothing, if you would call it. It's slightly more complex for a sensor that has multiple values to report, like the LTR559 lux and proximity. Here we have the sensor LTR559 class, which extends from the base sensor item and, as you expect, implements the poll function to the chip. Although it's essentially a sensor item with all the inherited functions, its role is to manage the communication with the chip, and the only function used is the poll. The actual values, lux and proximity, have their own classes and also extend from sensor item. This automatically gives them independent statistics. The only challenge is how to connect them to their manager. As you can see, this is done by passing their objects into the constructor of the manager, which then calls their poll functions, passing the data it retrieved from the actual chip. Creating the lux and prox objects in the main program and passing them in the constructor may look a little bit strange, but because the main program uses the val and stats functions of these objects extensively, it is more convenient to have these objects directly available in the main program. Going back to the actual code, you can see how this works. The constructor of sensor LTR559 initializes the driver and gets the lux and prox objects. The poll function gets the values from the driver and passes them to the poll functions of lux and prox. This val function here is actually never called, but just in case it might, it does something sensible. As a result, the main program calls sensor LTR559's poll once per second and can use the val and stats function provided by sensor LTR559 lux and sensor LTR559 prox as many times as needed in between. And speaking of stats, here's the principle of the statistics class. The new value comes in, and the first thing is to find if the new value is greater than the highest maximum so far, and if so, it and its timestamp are stored as the new maximum. The same happens to get the minimum. Next, the new value is put into the running average calculation, which uses an exponential weight function. This is set such that the weight of the value after 1 hour has dropped to about 0.1% of its original value, so it's practically forgotten and no longer contributes notably to the average. So far, these steps give us min, max and an average value shown in these boxes. Every 60 seconds, the average value is entered into a buffer that has 60 entries. You can see these like a delay line, and the internal value, oldest age, pops out, so to say, every time a new entry is entered at the front. Initially that value is just a minute old, but after running for more than 1 hour, the oldest age variable always contains the average value that is exactly 60 minutes behind the current average value. This process is now repeated in that every hour the oldest age value is entered into the buffer with 24 entries to give us the average value oldest D that will eventually be exactly 24 hours behind the current average. Then we repeat it again with a buffer of 7 entries to get the oldest W, which will be exactly 7 days behind the current average, provided the program runs long enough, of course. The way these buffers are implemented is using very efficient static ring buffers, so there is no copying of entries and no overheads from requesting or discarding of memory. Also, oldest is always valid even if the system was just running for a second, because the way the buffers are used and initialized. Until the system has run long enough to reach each of the buffer lengths, each of the oldest values will simply be the oldest available. The purpose of all this is to determine a trend by subtracting the oldest value from the current average. You can select whether to use the hourly, daily or weekly oldest for that. If the difference is positive, the trend is rising. If it is 0, it's the same, or falling if negative. This simple method works surprisingly well. In this actual recording of barometric pressure, you can see the noisy actual value in blue and the average in red. The yellow is the trend, simplified to just show +1, 0 or -1. You can see it ignores the small bump in the average here, and of course there is a delay before it catches the downward trend. That is because the hourly value is 3600 seconds behind and just about here where the sign reverses. I modeled this after what you would do naturally. Look at a value and remember that an hour or a day ago it was higher or lower, and thus determining trend. Rather than going through more than 1,000 lines of code, I like to highlight a few things that are new or significantly different from the code I shown previously for the Enviro Plus, starting with the LTR559. If you recall, the datasheet contains this statement, but no Appendix A, and search on the internet wasn't helpful either. Well, I decided to contact Light On Technology, and less than 24 hours later had the elusive Appendix A in my inbox. Here's the section with the Lux formula. As you can see, it's not exactly straightforward, and those values are probably numerical approximations of some curves they have measured. Gain and integration settings do play a part as well, as does a value called WinFAC, but I'll try to be careful how I pronounce it. If you have the bare die without cover, it is 1, otherwise it would have to be less to cater for the light attenuation when passing through the cover. I have no idea how much a laminated front sheet would attenuate. If you have watched my video on the front cover making, you will remember that I simply punched a hole through the foil for no other reason than to retain the factor of 1. Another way is of course to point a sensor to a light source without cover, then add your cover without changing anything else and see how much lower the reading gets. This could allow you to calculate the factor. My driver allows specifying a different WinFAC parameter in the constructor. The MEMS microphone continues to be a problem because audio and SPI are still not well supported by the Raspberry Pi operating system. You will see when we get to the installation section just how cumbersome that is. However, while taking ages to install, it's now working, and the code for using it is reasonably simple. Here's the pull function for the microphone sensor, and you see all it essentially does is reading a raw PCM value from a queue and converting it to dB SPL. However, there is this noise value you see here. the point of this value is to compensate for the fact that the reported PCM values are never zero, even in absolute silence. There is a DC offset as well as some system noise that prevents this. The problem is that I suspect that this value is system dependent. In my setup it's around 6700, but in yours it might be different. So there needs to be a way to measure it and set it for each Enviro station. This is where the configure function becomes useful. It allows you to set the noise value to anything you want. Most importantly, you can set it to 0, in which case the val function returns just raw PCM values. Then you run the Enviro station for a while in a silent environment, and the average PCM value should be your specific noise value. I'll cover later how to set that value in the setup data file. Down here you see that we're using a sampling rate of 16,000 samples per second, which means it ain't hi-fi, and frequency over 8 kHz are lost. But since we are mostly interested in noise, I thought that's a good compromise between audio frequency range and processor load. You can increase the sample rate if you must, but it becomes easy to overload the Raspberry Pi. All processing is actually done in the callback and follows what I explained in the previous Enviro Plus video about MEMS sensor. Essentially, the data is an array of signed 32-bit integers, and we are only interested in the maximum value, which could of course be positive or negative. Also, the microphone actually uses only 18 bits, and the division by hex 4000 or decimal 16,384 removes the padding the driver adds to make it a 32-bit value. Regarding the noise calibration, here you see an actual recording. I overlaid the blue ambient light plot to show that at least in our family, the only time it gets really quiet is unsurprisingly in the middle of the night. The only other sensor that has a configure function that actually does something is the gas sensor, which can be switched between reporting the raw resistance in ohms for each of the 3 metal oxide pads in the sensor, or to a resistance ratio if an R0 or clean air resistance has been set. I explained in the previous videos on the Enviro Plus that normally the manufacturer measures and documents R0 in special clean atmosphere individually for each chip, but for the Enviro Plus no data has been provided. So the only choice is to run the sensor in ohms mode in as clean air as we can find and take those resistance values as our clean air R0 values. But what I want to point out with this plot that it is far easier said than done. There are really large periodic variations in resistance, and if you compare those with ambient temperature, the curve in red, you can see a strong correlation. By the way, the aux sensor behaves exactly the same way, but its ohm value is relatively low, so it's difficult to plot together with the large values of NH3 and red. So while we can establish maybe a reasonable R0 for all, for example around here and here, it all goes wrong as soon as the air gets hot. Granted, 35 degrees Celsius is quite extreme temperatures, especially for the UK, but even here those heat waves seem to be occurring rather frequent these days. In any case, even for more moderate swings, the R0 is going to be affected. So while the current software allows setting R0 values for aux, red and NH3 and then displays the ratio, I have not worked out whether it's feasible to compensate for temperature, humidity and pressure effects to get a stable ratio, which we might then ultimately convert into concentrations in parts per million or ppm of certain gases. So that is all part of future research, as they say in any good scientific paper. With that, I think it's time to wrap the software topic up. It does not explain everything, but it should give you sufficient hints if you want to modify the code. The next video will show step by step the installation procedure, including the commands to download and configure the various packages from Adafruit, Pimoroni and my GitHub page. Thanks for watching.